I'd like to welcome everyone to another installment of our Sustainable Energy Seminar Series. If this is your first time, welcome. We're glad to have you here. If you've returning member of our Sustainable Energy Seminar crew, thank you again for joining. My name is Scott Williams. I'm the Education Manager at the Wisconsin Energy Institute and host of the Sustainable Energy Seminar. And this series is something that we do every other week in the fall and the spring semesters. And our goal is to highlight the cutting edge research that's happening across UW-Madison and beyond, and to showcase how different disciplines understand energy challenges and develop sustainable solutions. So throughout the series, we'll hear from experts in science and engineering, as well as social sciences and humanities, to learn about the ways in which they view sustainable energy challenges and solutions. This seminar is open to the public, but is also a course for students in the undergraduate certificate in engineering for energy sustainability, as well as the master's in sustainable systems engineering. And this seminar is only offered online through Zoom webinar. And if you registered for today, you'll be automatically registered for the remaining webinars this semester. This meeting is being transcribed, as you can see. If you'd like to toggle that feature, you can click the show captions button at the bottom of your screen. And if you have a question for our presenter, please use the Q&A box. If there is opportune time during the presentation to ask questions, I'll interrupt, but feel free to add your questions anytime, and we'll have time at the end also for questions. So with that, I'll introduce our presenter, and we actually have two presenters today. So first is Dr. Styliani Avraamidou, who is an assistant professor in the Department of Chemical and Biological Engineering here at UW-Madison. Prior to joining UW, she was a postdoctoral research associate and then an assistant research scientist at Texas A&M University's Energy Institute. And Dr. Avraamidou's research group focuses on expanding the limits of chemical and process systems engineering by developing tools for the understanding, analysis, and optimization of the interconnected circular economy supply chains. And this has applications for chemicals, plastics, and food. But as we'll see in today's presentation, also includes a focus on renewable energy transitions. And she'll be joined for part of the presentation by Javiera Vergara-Zambrano, who is a PhD student in her research group and also pursuing the Energy Analysis and Policy Graduate Certificate. Welcome.
Yeah, thank you for the introduction and for the invitation to give a lecture in this course. So yeah, I will be introducing you to the field of energy systems engineering, which is part of the field of process systems engineering that me and Javiera belong to. So what we will do today is go over mathematical modeling and optimization, techniques that can help us come up with informed decisions for the transition of energy systems. So Javiera will walk you through a case study that she's working on for our campus, and how we can use these tools that I will be presenting to come up with a plan for decarbonization of our energy system in the campus. And at the end, I will just show you some other applications of these mathematical modeling and optimization techniques for other energy systems. Okay, so I'll start with a bit of motivation. Of course, we know that energy is needed everywhere. We use electricity all the time, both for our day-to-day tasks, and then the industry uses a lot of electricity. We use a lot of heat, transportation. Our food systems need so much energy for water transportation, irrigation, fertilizers, cultivation, and everything. So yeah, energy is super important for everything we have right now. Okay, at the same time, there are a lot of people that don't have access to electricity, and then there are a lot of people that don't have access to safe cooking fuels. So yeah, we need it everywhere. It's not everywhere, although. Okay, how do we get today's energy from? And I'm sure many of you have seen similar plots to this one. This one is showing us the share of energy production by what the source is. So we have traditional biomass, coal, oil, natural gas. All of this is our fossil fuels. And then other newer technologies like nuclear, hydropower, wind, solar, biofuels, and any other renewables. So you see the share of renewables and fossil fuels in our energy mix. So how do we use this energy? Again, we use it for transportation, a huge part of it, industrial, another part. There's a smaller part for residential and commercial. And this is how we use it in the US specifically. Okay, so it seems like we have a lot of energy. We do tend to use more and more every year. And it seems that we are good in producing it, but there is something wrong. All of this energy that we produce creates a lot of greenhouse gas emissions. And we see here the amount of greenhouse gas emissions produced just from electricity and heating. Transportation is another huge part of that. And we can clearly see that there is a lot of emissions coming from the energy sector. So we know how to produce energy, but we are in a bit of trouble when we are trying to produce this energy sustainably. Okay, so can we produce sustainable energy? And I'm sure that you know about a lot of techniques and processes and infrastructure that we can use to produce sustainable energy. We can increase the penetration of renewable energy sources. The technology is there. We can do more solar, wind, geothermal, etc. We can improve the conversion technologies that we already have, our processes to become more efficient. We can introduce more heat integration to make our processes more efficient. We can even introduce technologies for CO2 capture and utilization that can help our energy systems become more efficient. And here I have a representation of some of the options that are out there. We have many different primary energy sources. Some of them can be renewable, some are not. Then we have conversion technologies like turbines, solar panels, gasification reactions. We can convert energy to either electricity or some energy carrier, for example, hydrogen or natural gas. So we can transport it throughout the country or from country to country to then use it at the end for the end use. So we have all these technologies. Some of them we use more than others, but when we're considering decarbonization or moving to a more sustainable energy system, it's not clear which technologies we should be choosing and which sources should we be utilizing where to put this facility. So that's what we are working on. The other thing is that should we just focus on greenhouse gas emissions? Are they the only challenge to our sustainable energy transition? And this is a diagram from FOAS showing different impacts that we should be considering when we're designing new systems, technology, supply chains, and so forth. And yeah, so greenhouse gas emissions is one of the environmental impacts, the carbon footprint, but that's not the only environmental impact that we should be looking at. Biodiversity, toxicity are some others. And then it's not just the environmental impacts. We should at the same time be looking at the economic impacts and the social impacts that will be affected when we come up with a new energy system or when we're in the process of transitioning to a new energy system. And then I think there is something missing still from this diagram that is trying to capture all of these impacts that we are after, and that's resiliency and robustness of the energy system. So I'm sure many of you have heard about the blackouts in Europe and Spain and Portugal, or the grid failing in Texas a couple of years ago, and the issues that they still have in Texas. So we want to transition to a system that is resilient and that we're not in a risk of losing power and risk of the grid failing with weather conditions or with demand fluctuations and so forth. So that's another objective function that we need to keep in mind. So we have the environmental impacts, we have costs, we have social impacts like job losses and so forth, and then we have also the resiliency of the electricity grid that we need to take into consideration. So multiple objectives there. Having that in mind, we need to come up with answers to a bunch of questions, and I have here some. So where should we produce the energy? Should we produce in a location that has a lot of sun and wind, or should we produce somewhere that there are a lot of people and need energy, or industries, or should we be transferring energy from one place to another? What are the best production technologies? What are the best conversion technologies? Should be storing energy somewhere? Should we be using batteries everywhere? There are so many questions, and each person developing a technology or company developing a technology might want to push forward that technology, but we're lacking a bit the tools to consider together all of these technologies and figure out what are the best pathways forward. Okay, so is this an easy problem to solve? No. So if we just take the US for an example, there are so many candidate locations to put in energy systems. There are different resource availability. So if we want to utilize biomass, we need to take the seasonality and the location of biomass availability into consideration. Natural gas availability is also varying from location to location. And we need to then consider all the transportation constraints and options, and all the demands of power and transportation all together to come up with an energy supply chain plan, essentially. So this needs to include all of our concerns and objectives that we just discussed. So environmental, social, economic, resilience objectives. We need to connect all of these pathways and technologies as a network. And then out of all these options, that will be a lot, we need to figure out how to narrow it down to a smaller set of best options that can fit our concerns and objectives and help us make these informed decisions. So the question here, do we just evaluate all of these options, or are we going to use any decision tool that can help us navigate this complex network of pathways that we have? And that's what the goal of this field of energy systems engineering is, to navigate all these different options and come up with best pathway solutions for energy transition. Okay, so yeah, it's called energy systems engineering field. What is a system? So if you look into definitions, you will see that the system is just a collection of parts. This can be elements, processes, entities that interact together. So one is affecting the other. And they produce some outputs based on whatever inputs we have. And in the case of an energy system, these elements can be your energy production units, your energy storage units, your energy transmission units, and all the connected parts are going to be the system. Okay, so from a mathematical point of view, we define a system as a set of equations that can describe the behavior of a group of related components. So what we do in this field is describe the energy system as a group of equations that will describe how the system will perform. And these are all pictures of systems. We can define a system as being just a car. All the components in the car, the engine, the steering wheel, the tires, everything there make the system of a car. We can have models predicting how all of these components work on their own and then connect them together to create a model, a mathematical model of the car. Then power plants, chemical plants, all of those can be defined as systems, and we can model the individual components and then connect them together. The same with maybe the gas transition pipelines that I have here. Okay, so then what we're doing is again modeling the energy systems. We develop models to accurately represent what's happening in reality. Then if we have this model of what is happening in reality, then we can test different modifications and alterations of that system and see what the output will be. So we can figure out optimized designs of that system without actually doing the changes in real life. What type of models we're using? We're using different types of models. So we have models at different scales and different levels of accuracy. The first principle models are models that use actual physics and chemistry to describe what is happening with a device, a unit, an element. Black box models are models that just use data. So if we have a system and we have a lot of input and output data, we can train some black box model that doesn't know any physics, but then it can kind of predict the outputs based on these data that we have collected. And then we have hybrid versions where we use both data and first principle to come up with models. Okay, so the other thing that I alluded to is the multi-scale nature of that. We have models of different scales to describe the entire energy system. So we're going from materials and units all the way to plants and power plants, and then connecting all those together to energy grids and energy supply chains. So we can use all these tools to analyze at the different levels, but then also connect those levels together to come up with energy planning solutions. Okay. Again, this slide is showing the different things that we need to take into consideration when we're building these models, and the fact that they're multifaceted. We take material information all the way to how the energy is distributed through the electricity grids, so the actual supply chain of energy. Okay. So the models that we develop in my group are based on this multi-scale aspect. So the two scale, we're considering only two scales. The rest of the scales, we have models from other people that we can use. But the scales that we do consider is a short-term modeling, which is deciding the scheduling of our energy use, energy production, energy storage devices, which usually is at the hourly scale. So we have models that predict how the operation of energy devices and devices that participate in energy supply chains operate at the hourly scale. And then on the long term model, we are coming up with infrastructure planning decisions. So building or decommissioning infrastructure in terms of energy supply chain at the yearly level. And this can span many years, like 30 to 40 years. And that's the case study that Javiera will talk about in a bit. So yeah, the reality is that we can build these models, we can get solutions, but that these solutions will be good for maybe the economics or the environment or the efficiency, so we can define an objective function. But then we need these engineering tools that I will be talking to you about now to come up with trade-off solutions. So we build multi-objective optimization formulations where we can simultaneously consider economics and environment and get a trade-off solution in between. And I think Javiera will show some of those in a bit. Okay, so then I just said that we have all these different solutions. How do we narrow down the space of solutions? How do we pick up some of these in the vast majority? Should we just do exhaustive enumeration and just evaluate all of these points? no, what we're doing is this intelligent decision making through energy systems, which is the final part that I will talk about, is using data analytics and optimization to come up with a solution to our optimization problems. Okay, so those are the tools that we're using. We use a lot of data analytics, input and output data, both for the modeling part and then the optimization part. And we're trying to make sense of the data, get any trends that might be happening that we cannot see from a naked eye, and use that to find optimal solutions. And then we build this mathematical optimization models and simulation to describe our systems. The final will be the optimization. I think Javiera will have some slides on the campus for that, where we're giving an objective function value that will be our economics, environmental aspects, or social aspects. And then we're putting as constraints the description or the models that we have for each of the energy process units. So we have an objective, a set of constraints, and then our design variables are how to operate our energy units, and if we are going to build or decommission any energy elements. Okay, so all of this together are making what we call the energy systems engineering. Here I have some relevant literature on that, and a schematic representation of our framework. So how are we actually doing that? So we need to take into consideration the area that we are interested in. This can be an entire country, or a state, a county, a small city, our campus. So whatever size this might be. Then what are the technologies that we have as options for both producing energy, converting it, storing it, delivering it, all of this. Then what is the weather data? What is the past hourly data for that region? And then what are the demand profiles for both electricity and heat, or whatever other type of energy we're interested in that region? And then any type of objectives that we want to capture. Then we build models for the different elements that we combine them together, we solve the optimization problem, and we're able to find different solutions based on our objective functions. And these different solutions can tell you when to build something, how big it should be, what are the actual footprints and impacts of these moves that you're gonna do. Okay, so this is my final slide before Javiera comes in and gives her example. The other unique thing that we're doing compared to other energy planning works is that instead of considering only one type of demand that might be just electricity or just heating, we are integrating these energy demands together, because we know how interrelated energy systems are. So if we are changing our heating systems to be electrified, then that will directly change the demand for electricity. So we are integrating this together to consider both heating and cooling and electricity at the same time. And therefore, we're able to come up with these a bit more complex models, but capturing all the different pathways and decisions that we need to make for energy systems. So I'll now stop sharing and let Javiera share and talk about her case study on the campus energy transition.
Okay, can everyone see it?
Yep.
I can
Okay,
see.
yeah.
Yeah.
Okay, perfect. Yeah, so what I'll be talking is how we apply all the system engineer tools into a specific case study in our campus. So I will start by sharing a little bit about how the energy is fulfilled in our campus. So this is a map. We can see maybe if you have walked through like the south of campus or the west, you can see like a steam cloud. Well, that steam come from our heating and cooling plants. There are 3 plants on campus, one on Charter Street on the south, and 2 on the west. One is Walnut, and the other is West Campo cogeneration facility. West Campus also produces electricity, but is currently like all the electricity goes to MDNE. And all these three plants are fueled by natural gas. So we have a heating and cooling system that mainly runs with fossil fuels. On the other side, we have the electricity supply through Madison Gas and Electric, having their own goals. And there's also an incentive to install more renewable on campus. We have some rooftop solar in Gordon Dining Hall, on the Avraamidou Visitor Center. And there's also the Bryan Solar Field, which is the university is part of the renewable energy rider. So they obtain carbon credits through them. But the reality is that less than 0.1% of the campus electricity usage is generated from renewables. So there have been a number of initiatives, and in fact, last year you must heard like UW launches all the sustainability initiative, and I want to focus particularly on the second one. This says procuring 100% renewable electricity on campus by 2030, and also achieving net zero emissions by 2048 or sooner. So our current situation is not great. We have like a system that mainly relies on fossil fuel, but our real question is, what do we need to change? What are the infrastructure changes required to achieve net zero emissions? And that's where like tools and our field comes with. Let's like propose new like alternative. Let's study, let's see what's bad, let's see like the trade-off about them. So that's what we are currently trying to do, and that's what I've been working the past couple of years. So let's start first about like how we do it, what's our idea, what goes behind. When we think about modeling energy, we really talk about problems that have like million of variables. And this is because we need to model sometimes like hourly. We think like the number of hours in a day, the number of days in a year. We're talking like each variable, if we only model a year, could have like 8,760 like steps. And that's only one variable. So we have million of variables, millions of constraints. This is like really difficult to solve. So what traditional approaches have done is use this approach called representative days. So we have like energy profiles, we have like weather profiles, and what we would do is trying to group certain days, defining certain like criteria for similarity. So let's say we form like 5 groups. We can separate all those like energy profiles in 5 groups, and then for each group we will find one trend for it that will represent it. That's why it's called representative days. So we can say like we have like 5 days that will represent my whole year, and we'll have like a percentage of how many days it happens in a year. This approach is very useful because it could like reduce the size of my problem, but it has certain like cons also, and one of them is I will lose all these extreme events, for example, all these peaks here, or if I have no energy like demand, or I'm not producing energy, I don't capture this with this model. And this is specifically important when we talk about storage. When we think about storage, we think about like a box, and the only way knowing how much I have is knowing what did I have the previous step. So I really need like the accuracy and having like a full resolution when we are modeling storage. And that's why our approach is more talking about like full hour resolution, where we are trying to model more realistic storage. We are also trying to capture like the full variability of renewable particularly. And we also want to try it for multiple years. We are interested in seeing like short-term solutions and also long-term solutions, and how like the investment will affect the operation, but also how operation will affect the investment. So why this matters and why full hour low resolution matters. What I show here is a dot curve, and this describes how like the net electricity changes through the day. So what is the net electricity demand is the total demand minus the renewable generation. And this is like in California, particularly with solar. So what we have in the morning is the demand rises as like people wake up, like you start using electricity. So that's why we have the peak here. Then what happen like midday is like we have a high solar generation and we have like a lower demand. So that's why like here it drops. And in the evening, again, like solar generation falls and then the demand rises again. So this looks like a dog, like a curve. And what challenges brings this is like we have like an overgeneration during the midday. We have like to ramp up in certain points and we need like certain flexibility. So we really need to capture all this variability, especially when we consider renewable energy in our models. And if we want to have like a reliable system in the future, we need to account for this. So let's go back onto how the tool works, and very simple works is we start with about the characterization of the urban area. And here I show what's actually the demand off campus. And we'll start seeing like we talk about electricity is real like we can say flat compared to what's heating and cooling. And this is really important to like propose solution is like when do we have like peak demand? What type of demand do I care more in each season? So we identify energy requirements. We also look for what's the current infrastructure and what's the future infrastructure. And we do also like weather collection and demand data generation. So we try to use like weather stations to use like real data of the areas we are modeling. Then we go into what's the mathematical modeling. So we have what's the current infrastructure. We talk with stakeholders about what are the options they are looking for. And then we propose all the alternative. When we talk about optimization problem, we talk trying to find the best solutions, but we have like a number of alternatives. As Styliani mentioned, we use this like multi-scale approach within this type of tool is like we look like decisions are hourly when we talk about like supplying the like matching the demand. We talk about like annual decisions that or could be like every couple of years for investment and then like long term like reaching net zero or reaching like a certain like target of emissions. So what the mathematical model looks like will be like minimizing either costs or minimizing emissions. And we want to like satisfy the energy subject to like what the capacity of each plant, what like operational constraints of the equipment, and what's like the land that we have also available. So we want to find the solution, we want to find the capacity, the energy produced, and all these factors. And then this problem, once we say it, we go into the implementation and solution. So the strategy we follow is we will first talk about single objective optimizations. What this means is we look only on minimizing costs or minimizing emissions, and then we go with like what if we care about both? What happened? That's called multi-objective optimization, and then we do some sensitivity and a scenario analysis to see like trade-off and what parameters affect more our problem. So I will show you now what are the main results we have gotten for like the case study and the campus. And the first thing, like looking about the goals and reaching 100% renewable electricity in 2030, we found it was not possible. And this is because MGE will not reach 100% renewable electricity in 2030. So we really need to align our goals and work together for this. So that's one thing to consider in this type of problems. And when we start saying like, okay, we want to have a reliant system and that's why we need the grid. And we see like the path of the grid with one of the questions we start thinking about what was like, okay, we will rely 100% on the grid or what happen if they have a delay, how will affect us. So the other scenario, maybe a little bit extreme, is like it has no improvement. So how the grid decarbonization really influence what are the infrastructural requirements. And that led us to start like 4 scenarios where we think about like, okay, we care about minimizing costs, we care about minimizing emissions, but let's consider also in a scenario when we reach net zero emissions, MGE reaches net zero emissions, or a little bit more pessimistic where it's like that is a little bit lower. So what we found and what type of results we can get with those tools is we can analyze the energy mix. So we start seeing like what's our current scenario. We either have electricity coming from the cogeneration facility or from the grid. If we look at a more optimistic scenario, we want to reduce emissions, we have a higher penetration of renewable. But if we look to minimize this cost, it's also convenient to install renewable. So that's a good thing. We have also economic incentive to install renewable energy. In the case is a little bit more pessimistic, then we rely a little bit more on the grid, but we also want to solve renewable energy. So that's important. Like we have also economic incentive. Other type of results we can get and we can track is talking about what are the costs, the annual costs, how much more expensive will the system be, and why this will cost me more. And then we can talk about big numbers. It's like, okay, my investments this year will be this much, but we can go deeper into like, okay, which technology will contribute more here? And what we found is like, okay, we need more renewable energy in terms of cost, we have benefits. In terms of emissions, we have benefits, but we need a lot of storage. And we found like around 40% of the cost needed for the system in the next 25 years come from storage. So an important point is how this like technologies develops, like batteries or any other type of storage. And the third type of results we can get with this tool is talking about operations. So we talk about like investment. We also go into like how it operates, how we specifically this goes into how we use the current infrastructure. So I want to show the case that is more interested going about cooling. Right now, what we have, we use natural gas. So 100% like every day goes with natural gas. When we go into like 10 years, let's say, we see a change depending on what we care more, if we minimize costs or emissions. We see this change from natural gas to renewable natural gas. This means like in every case, we are still using our current facilities, and that's important because decommissioning a facility, one is expensive, and the other thing we cannot just like shut it down because we want to like use our technology. We have to consider all the other impacts that go there. And then if we go into like 2050, let's say 25 more years, we start seeing other changes, more electrification. So we see like short-term solutions, we use natural gas, renewable natural gas. Long-term solutions, we start with electrification, and that goes on like aligns with like the electricity will have less emissions. So really what the grid decarbonization will influence our infrastructure, and we have to also consider what the current infrastructure of our system is. And the last thing I want to like go into is let's analyze the trade-off. And one of the questions here comes is how much more expensive will be to reduce like a certain amount of emissions. And with optimization, we can build this type of figures that is called the Pareto front. When we have emissions and we have costs and we can analyze the trade-off. So basically how we can read this is like we have here the baseline on the top. And we ask a question, well, if we reduce emissions, how much more expensive will it be? And we see it's around like 30%. So this can let us like how the budget will be, what's the influence of the budget. So we have on the top end, we have higher emissions because we rely mostly on fossil fuels like natural gas. We have up the top end, we transition more into renewable natural gas and other renewable resources, and that's why emissions lower, but that also comes like with higher costs. So we can analyze different scenarios with this, and the main conclusion is we need to balance costs, emission targets, and also what's the land efficiency to specifically install all the renewable energy we will need. So the main conclusions we have come up is really the importance of temporal granularity and the insights it can provide that. We have 4 campuses in specific, like a switch in the next 5-10 years to renewable natural gas would make a huge impact. Of course, there are like policy that are required for that. And in the long term, we need to electrify the system, or it will be a good idea but only if we can have renewable energy for electricity, of course. And the other thing is thinking about the grid and how it influences our system and all the effort that stakeholder has to do together. So with that, the next word says, Selena, I don't know if you want me to keep sharing.
Yeah, keep sharing because it's just the
Yeah.
slides. Yeah. Okay. If you want to go to the next slide, I have some other examples here of how we use these similar tools to tackle different problems. This project funded by NSF is looking at how we can use chemical devices and electrochemical devices to help with the electricity grid balancing. So participating in electricity market essentially and getting the profits from the electricity markets for the chemical industry while at the same time allowing for more renewable integration. So again, this is kind of a planning problem, figuring out what devices will be best to be used to hedge the power grid and where should we be locating them. If you go to the next slide. Yeah, so this is another project on energy. So we're looking at energy carriers. The project here is trying to figure out if ammonia is going to be a good energy carrier or not. Some experimentalists are working on this project trying to develop ammonia fuel cells, so using ammonia directly to convert to electricity. And then what we do in our group is model all the different pathways for competitors to this technology. So we're modeling the production of hydrogen, using hydrogen as an energy carrier, using just petroleum fuels and so forth, and then coming up with a set of parameters for the experimentalists to tell them, okay, your device should have this much efficiency and be cost this much in order to be more competitive with the rest of the technologies that are already out there. Next slide. Okay, this is a similar one. Here we're working on a different type of energy carrier. This is actually a hydrogen carrier. So we're instead of liquefying hydrogen and transporting it in pipelines or pressurizing it in cans, what we do is convert it or add it on a biomass-based carrier. Which will be liquid in room temperature and pressure. So then we can handle it as we're handling the current petroleum-based fuels. So we can transport them in pipelines or tankers and so forth. So here again, we're looking at the entire supply chain of the competitors plus the technology that we are interested and then trying to figure out what will be the targets for this technology to be better and for the supply chain to actually want to transition towards this technology. Yeah. One more. Okay, so that was it. We thank you for paying attention to us and let us know if you have any questions. Javiera's project is funded by WRF, and some other things that I've shown here have been funded by NSF. And then we got a lot of data from the facilities and planning and management office at the UW-Madison for Javiera to be able to complete her case study. So yeah, thank you.
Thanks, you too. Yeah, so please put any questions in the Q&A if you have any questions. And as we're waiting on that, I guess I had a couple of questions. I'll start off with one I had. So, we've seen in recent years, massive declines in the cost of solar and batteries. So how do you account for, things like technology change over time in your modeling to kind of feel that you're still maintaining accuracy?
Yeah, so some technologies do have like a learning curve to them. So maybe their efficiency is getting better or their cost is getting down. So that does appear in our models. I'm not sure what is happening with Javiera's models. She can say it directly, but yeah, for other models, we do that. But then you're never accurate in terms of like cost and efficiency. Like we have so many input parameters that go into these models that we don't know the exact number. of them. So it's very important at the end of all of this analysis to be doing what we call the sensitivity analysis, where we test different scenarios, say, okay, what if my cost is off by 10%? What if my efficiency is off by 15%? And see if the solutions are changing or not. And if they're changing, it means that we need to look further and figure out maybe what these parameters are, or if that second solution that we're finding might be even more robust than the first one. So Javiera, do you want to say a bit about this?
Yeah,
Your model specifically?
yeah, the model considered changes through time. Since we're modeling 25 years, we see changes every year. But it's also important, like the trade-off we see with land. Like we see, like if we minimize, that's why my model like minimizes cost and emissions, because there's also like land efficiency that is important. Like in this moment, like wind, like in terms of like kilowatt hour produced could be cheaper, but it uses way more land. So that's when like all this trade-off, and that's why we want to like minimize costs on one sense and minimize emissions. And we can see like how like cost affect, but also like land, and we can talk about also disposal or other factors could affect. So that's all I count in the model.
And actually, that's a good follow question I had on when you're considering those different, land use impacts. For this case study, are you looking primarily at land on campus, or it's UW procuring, a share of a power plant somewhere where it's not necessarily university property, like in the case of the O'Brien solar field?
We are considering just like university land in terms of producing. The other like future step is analyzing like carbon credits in that case.
Okay, great. Seeing any questions here, but can give folks another minute or two if they do have any questions. I guess you stumped everyone. Well, thank you so much for your presentation. It's really exciting to see, the application of this to our campus energy decisions. So thank you for the work on that.
Thank you.
All right. And thank you all for joining us. We'll have our next seminar in 2 weeks on Monday, and we'll talk more on transportation systems this time. So I hope to see you all there. Thank you.
Bye.